Let's take a look at exponential growth and decay in a continuous model here. We're given the equation y equals a, which is the initial amount, times e to the negative k times t in decay, or in growth it would be to the positive k times t. Now, what t is the time in years, k is going to be some constant that determines the growth rate or the decay rate. In the case of carbon half-lives, we'll be given the k value, and other problems will be asked to calculate the k value given everything else. So let's take a look at this first example. Paleontologist is examining the bones of a woolly mammoth. He estimates that they contain only 3% as much carbon-14 as they would have contained when the animal was alive. How long ago did the mammoth die? What they're doing here is they measure how much carbon-14 isotope is left in an animal, and depending on how much is left, they can calculate how long ago the animal died, because when it was alive there was more. So let's set up this equation. Y equals a times e to the kt, and we know that our a is our initial amount. That's going to be, well, they don't tell us an initial amount, so we'll just assume that it's 100%, or 1.0. The final amount that we're left with, which is y, is 3%, so 0.03. So whenever you're given a percentage like this, where it says only 3% was left at the end, you're going to have your initial be 100%, or 1, and your final be whatever your percentage is as a decimal. After that, k, we're going to use the one for carbon half-life because this involves carbon-14. And so we're going to use that k equals 0.00012, and then t is what we're trying to figure out. So t is the unknown. Pop these into our equation here. We're going to have 0.03 is equal to 1 times e to the 0.00012 t. Want to clean this up a little bit, so I'm actually going to get rid of that 1, because multiplying by 1 obviously doesn't do anything. Then I need to undo my natural number as my base here. So to do that, I'll take the natural log of both sides. So on the left side, I'm left with natural log of 0.03. On the right side, the natural log of e cancels out, so I'm just left with my exponent up here. And that's going to be 0.00012t. Divide by that large constant, or very small constant actually, on both sides to get t by itself. Pop it into your calculator, and you will find that the value is negative 29,221. So what that means, approximately, is that the mammoth died over 29,000 years ago. And that's how they do a lot of these carbon datings, when they put dates on when they found prehistoric bones, dinosaurs, things like that. Next example. We are looking for the half-life of sodium-22. They tell us that it's 2.6 years. They want to know the rate of decay, the k value for this sodium-22. So we start with our basic equation, y equals a to the e, or a times e to the kt. Since we're looking for a half-life, we're going to assume that our initial amount is 1, and the amount that we're left with, y, is going to be half of that, 0.5. So just like the last one where we had 0.3 as our, or 0.03 is what was left over, we have 0.5 as what's left over. K is what we're trying to find, so we're not going to know what k is this time. We can't use the carbon-14 one. So k is our unknown, and t, they tell us that it's 2.6 years, so we're just going to use t equals 2.6. Pop these into our equation. We have 0.5 equal to 1 times e to the k times 2.6. Get rid of that 1, clean it up a little bit. Then we need to undo our base e. So we take the natural log of both sides. Natural log of the left side, ln 0.5. Natural log of the right will get rid of that base, and we'll be left with just 2.6k. Finally, we divide both sides by 2.6 in order to get k by itself. Pop in your calculator, and you're going to get negative 0.2666, approximately. So that's going to be our k value. That's going to be the final answer that we are looking for here.